Okay. Well,
Okay, welcome everybody to the afternoon session. This is Jos Uffink from the University of Minnesota, and he is going to talk about Schrödinger and the prehistory of the EPR argument.
well, thank you very much. I'm delighted to be invited here, and it's also my pleasure to dedicate this talk to Gerard, who has always maintained a profound interest in the foundations of physics and quantum mechanics in particular, as we just heard about the book on the implication of quantum mechanics. My talk will be more or less historical on this topic. This is joint work that I did with Christoph Lehner, in particular on deciphering some of Schrödinger's unpublished letters and notebooks that are actually now online and can consult them from a website in Vienna. And I wanted to talk about Schrödinger's role in the development of the Einstein-Podolski and Rosen argument. Now, I assume that for an audience like this, it is rather superfluous to try and explain the Einstein-Podolski-Rosen or EPR paradox, or argument as I will call it, because it's so familiar. But in case you, just to refresh your memory, the argument is about a pair of systems that have interacted in the past and have then since separated, and they're sent to different sites, and one is, that's Alice's, and the other one's Bob's. Those two systems are in what we now call an entangled state, in fact a maximally entangled state, which is such that both the positions of the two systems and the momenta are strictly correlated. And then as a result, if Alice measures, say, the position of her particle, she can completely predict what the momentum of the other particle is going to be without ever touching that other particle. According to the EPR argument, precisely because you can completely predict the value of that other position, there must be an element of reality corresponding to that value. On the other hand, if Alice decides to measure momentum instead, then by the same correlation, she can predict the momentum of the other particle, which then should also correspond with an element of reality. And then there is a more or less implicit argument that whatever is real for the second particle cannot possibly depend on what choice of measurement Alice makes very far apart. So the upshot is then that that second system must have both a value for its position and momentum, but since quantum mechanics doesn't contain any description of a system for which both position and momentum are viewed, therefore quantum mechanics must be incomplete. That is the argument in a nutshell. Now, that paper was published in March 1935, and as I said, it discusses this pair of particles using an entangled state, although that word didn't exist at the time. It was actually Schrödinger who, in the fall of 1935, published two longish papers on this argument, who introduced the term entanglement or Verschränkung in the German original to denote that situation, and who pointed out that this was actually the key ingredient in which quantum mechanics differed so much from classical physics. He also formulated his famous cat paradox in that context, and together those works of Einstein, Podolski, Rosen, and Schrödinger had a profound impact on the discussions of the interpretation of quantum mechanics, because they refocused that discussion from uncertainty relations and complementarity that had been the mainstay before that, to the notions of entanglement and later on especially locality that now dominate that debate and that indeed led to now to technological applications in information processing. Historians have often believed that it was the EPR paper that triggered Schrödinger to work on the subject, and in particular Arthur Fine, who wrote a book on the EPR argument in 1986, and has a whole chapter on correspondence between Einstein and Schrödinger over the summer. Arthur Fine argues that Schrödinger's ideas were more or less developed in response to the letters he received from Einstein. I want to push back a little bit on that picture in which Schrödinger is more or less painted as a passive receiver of the brilliant ideas of Einstein, and argue that Schrödinger played a much more formative role in the very development of the EPR argument, and that essentially he had that whole argument already in 1931. So let me first go back to what is known about the prehistory of the EPR argument, where it came from or where it started. It is clear that in 1930, Einstein presented his famous photon box argument at the Solvay conference in Brussels, and we don't know exactly what that argument looked like because he didn't preserve a record of it, but the best we know is Bohr's after the fact reconstruction of that discussion, which he published in 1948, which is 18 years later, and as we will see, Bohr's reconstruction might not have been completely faithful. But here is a sketch from Bohr's paper of the photon box. What you see here is a box that contains a timer and a shutter that will open a slit in the box for a very brief interval, and in that interval one photon is supposed to escape from the box. At the same time, the box is weighable, is fitted on a scale here, so that if a photon is emitted, you can actually determine the mass of the box that is missing and by weighing it, and thereby determine the energy of the photon that has escaped. Now, the way that Bohr presents this argument is as if Einstein had tried to beat the uncertainty relation for energy and time by arguing that since the slit is only open for a very brief interval that we can know precisely, we know the time of departure of the photon. At the same time, we can measure the energy that is missing from the box very precisely if we wish, and so we would be able to determine both the time of departure and the energy of the photon, and thereby contradict the uncertainty relation. And then Bohr shows how this argument is actually defeated by pointing to the gravitational redshift formula, which then makes the affects all the apparatuses in the box, and therefore also makes the timing of the shutter or the clock mechanism uncertain, which would then come to his rescue and save the uncertainty relations. As I said, Bohr's reconstruction is slightly misleading because we know that from a letter that Ehrenfest wrote to Bohr in I'm missing here. I think it's from July 1931. Ehrenfest has just met Einstein, and Einstein told him that he had absolutely no doubt about the uncertainty relations, and that he had by no means intended this photon box or weighable light flash box, as Ehrenfest called it, as a counterexample to the uncertainty relations, but for a very different purpose. And then there's a piece missing here. He describes that purpose as to build a machine that emits a projectile, and then after the projectile has left the machine, you have a choice in either reweighing the box and thereby determine the energy of the photon, or by opening it and inspect the timing mechanism and thereby determine the moment of escape of the photon. Einstein was very clear that you couldn't do both at the same time, but since you had a choice of measuring either one or the other, you could predict two properties of a particle which was far away, and therefore both properties must have been real for that photon. So what you see here is already a skeleton of the EPR argument, which, according to Ehrenfest, was already present in July 1931. So the logic of the photon box argument that Einstein gave in 1930, or at least that's if we believe Ehrenfest that this was the original intention of Einstein, must already have been very similar to the EPR argument. However, although the logic indeed is very similar then, the details are very, very different. In fact, the photon box, I would argue, contains so many distracting features that it's still an important step to get from the photon box with all its shiny details to a lean and clean example that is the Einstein-Podolski and Rosen argument. For example, by trying to determine the energy of the box by weighing it, Einstein, of course, refers to the equivalence principle of general relativity. And that invites numerous discussions about what the relation between general relativity and quantum mechanics is going to be, if those are to be combined into a single theory, and also, of course, whether Bohr was correct to employ the gravitational redshift formula to save the uncertainty relations. As I say, I think this is a distracting issue because all those things can be avoided, and they're not really essential to the argument, but they have been the cause of many papers in the literature. Another issue is that it focuses on the energy-time uncertainty relation, which invites the problem whether time is a proper quantum observable, and whether there is an uncertainty relation for time and energy in the same way as there is for position and momentum. And again, I'm not going to say that those problems cannot be solved. In fact, they can be solved in many, many different ways. And again, there are hundreds of papers on that issue. But what I'm trying to argue is that this whole issue can be avoided. And the last difference that I want to emphasize is that in the photon box argument, there's only discussion of uncertainties in qualitative terms, and one never discusses the argument in terms of the wave function or quantum state, and therefore there's no natural place where something like entanglement could appear in the argument. So that again is something which is missing from the photon box argument and which is present in the EPR argument. So, as I said here, in contrast, what the EPR argument does is it uses just plain old, good old quantum mechanics, non-relativistic. It just talks about two systems, there can be particles. there's an entangled wave function, and there is indeed the same kind of logic, namely that you can have a choice of measuring either of two incompatible quantities on one particle, and then predict something about the other particle, and so on. We also know that in April 1932, after Ehrenfest again nudged Einstein to try and simplify the photon box argument to something simpler, in particular to use wave mechanics, or I think what he means is non-relativistic quantum mechanics. And then Einstein gave a simpler version in terms of a collision of a photon with a mirror, doing away with all the weighing and the box part of the argument. Now, you might ask yourself, how did Einstein get there in April 1932? Well, here is Schrödinger writing in December 1931 to Sommerfeld, and I will quote more or less extensively from that letter, where he writes, "The foundations question torments me more and more, and unfortunately completely fruitlessly. May I babble a bit to you? Darf ich Ihnen etwas vorschwätzen?" We have been debating for hours in the seminar about the following actually quite simple case, taken one-dimensionally. So here's a mirror, heavy mirror, and a photon, or Lichtband, as Schrödinger calls it. On a heavy mirror, we measure its momentum very precisely, and simultaneously the position of a photon, also very precisely. The color of the photon and the position of the mirror are therefore very uncertain. Then I let the photon reflect on the mirror. It thereby absorbs twice the momentum of the photon. After this has happened, and when the photon is a good distance away, I have a choice of measurements on the mirror to determine either the position or the color of the photon. Namely, if I measure the position of the mirror, its value will be the same as the position at which the collision occurred, and enable a very precise inference about the position of the photon. But when I decide to measure the momentum of the mirror, then I can, because its initial momentum was known, determine the color of the photon. Admittedly, I cannot learn both position and color of the photon simultaneously, but I can learn, without interfering with the photon, either one or the other, whichever I please. Even more amazingly, our mirror is a universal instrument for the positioning and color of the photon in the following sense. When the photon is treated in the way above, both position and velocity of the photon leave a trail on this instrument, and both will be registered with accuracies whose product falls far below the limit of Planck's constant. Both trails really exist because it depends on the decision of my free will to use one or the other, although then the second one is washed out. Because the photon has nothing to do with the manipulations on the mirror, I can hardly say that its sharp position or its sharp momentum is only created by one of those manipulations. In any case, this is not a creation in a real, but at best in a mental sense. One would like to conclude that the photon always possesses a definite position and momentum, a view that we have long ago abandoned as paradoxical. The only way out, it seems, is by something like this emergency decree. In quantum mechanics, statements about what is real, about the object, are forbidden. They deal only with the relation object-subject, and apparently in a much more restrictive sense than in any other description of nature. So, in this letter, Schrödinger already had almost all the ingredients of the EPR argument. We have a choice of measuring one or another of two and non-commuting observables on the system, thereby allowing an accurate prediction of the other. there's an argument that goes on that those properties must be real, and that they really exist, the trails that are left behind. And although we can do both at the same time, these predictions must correspond to physical reality. The only differences are, first, that Schrödinger never draws a conclusion in terms of the incompleteness of quantum mechanics, and this is something that will remain characteristic of Schrödinger's position.
Sorry, this is Einstein.
No, this is Schrödinger.
Oh, I'm sorry.
Schrödinger writing to someone.
Oh, I'm sorry.
Yeah. And there is also no mention of an entangled wave function to back the argument. By the way, you might be interested in how Sommerfeld responds to this query, this worry that Schrödinger had, and he had very little to say about it. He says that he had given the letter to Hans Bethe, who was working with him in München. And the only response that Hans Bethe gave was that Schrödinger had been a bit sloppy in using the terms momentum, velocity, and color of the photon. And indeed, of course, you have to distinguish between momentum and velocity. But apart from that minor terminological remark, they have no answer or reaction to the whole problem. So, Schrödinger has already analyzed the situation of a mirror and a photon that are reflecting in December 1931. You might remember from the start that he referred to a seminar where they had been discussing this for hours. And you might wonder, at least I did when I saw this letter, what was that seminar? Well, fortunately, there's I think it's a journal for chemistry in Germany, who duly published abstracts of talks that were going on, certainly in Berlin, also in other parts of Germany. And here it is, a short summary about a colloquium that took place in November 1931 by Albert Einstein under the title about the uncertainty relations über die Unbestimmtheitswerte. And this abstract, which was not written by Einstein but by the correspondent of the journal, you can see that he talked about the photon box. There's a box there that has a shutter that you can open, and you can try to measure its weight by a weighing device. And there's a photon that escapes, or a monochromatische Lichtstrahl. And then he has a mirror to be placed many light years away, which will reflect the photon back to the site of experimentation. And then again, there's a choice. You can either determine the time of escape of the photon, or you can try to re-weigh the box and therefore find out what the energy of the photon is. It's clear that Einstein does not intend to use those two simultaneously. He is absolutely clear that one can only do one of those two measurements. But since the photon cannot possibly depend on what choice we make on the box, it should have both of those properties independently. Now, the role of the mirror here, I take it, is only for rhetorical purposes. It means that the photon is underway for many years and then will come back to us many years later. And in the meantime, we have ample opportunity to reflect on what second measurement we can do. And if those measurements, if they are to be accurate, require a lot of time, then we will have all the time in the world to do so before that photon will return. Other than that, I see no particular role for the mirror. Now, so this is more or less what I said. Einstein discussed the photon box argument in the sense that we have already seen that Ehrenfest reported on his thinking. And Schrödinger was clearly present at that seminar. Of course, they were both colleagues at the time in Berlin. And those notes have also been preserved. And here they are, under the title Bohr-Einstein Beispiel, for example. On the left, you can see a sort of schematic picture of the box with a shutter and a weighing scale. Then there is a mirror, and above the mirror, Schrödinger has written the word Sirius, which means indeed it's very many light years away. Then the photon will come back and enters a prism to be counted in a photo tube. Now, I won't show you all of the handwritten scribbles that Schrödinger wrote on the unit, but from them you can learn that Schrödinger was actually critical of Einstein's argument. He was not convinced about this photon box argument, and in particular he pointed out that it is not allowed to assume that you can have a device that will, like a shutter, that will open something in a very short while, which means quantum mechanically that it would have to go from one state to an orthogonal state in which the shutter is either open and closed. Do that in a very short time, and at the same time have a determinate energy for the whole system. And indeed, that is one of the formulations of the energy time uncertainty relation. But there are other notes which presumably come from the very same day. Here is a page that discusses the mirror in the light quant, like the photon, in very same way as he later wrote to Sommerfeld. And then you can see a discussion of the uncertainty relations. And although the page doesn't end with a clear discussion, with a clear conclusion, clearly he analyzed this argument, and the page ends with a question saying, this is how it goes for light, how will it go for particles? Well, there's another document, and this time it's 8 pages long, also from the folder Szilard Spiegelmessel, 1931, which is much more interesting. This one is dated November 4, 1931, but if you look more closely, you will see that the original date was November 5. And here you can see how difficult it is to read Schrödinger's handwriting. Het handelt zich volgende gestern van Szilard in colloquium aufgevoerd vragen. I will skip the rest and give you a translation. So here's the question that Schrödinger asked. We have two systems, S and S prime, and they're separated. Is it possible, by an appropriate choice of measurements on S, to make one or the other of two conjugate variables, A prime and B prime of S prime, sharp in the sense that the product of their unsharpnesses is less than Planck's constant? Then he analyzes that question, and he first puts it in a more formal form. I've used here Dirac notation to be more, since that's more familiar nowadays. But he asks here simply, is it possible to have a quantum state in such a way that it has a bi-orthogonal decomposition in two different forms, one in which the eigenstates of the quantity C are used for the first system, and another one in the eigenstates of quantity D, and for the second particle, the eigenstates of A prime and B prime. So yes, is it possible to have those two decompositions? And then he discusses that problem by starting out with the first conjecture that the answer is no. And then he tries to prove that. And he uses 3 different methods or strategies to try and prove that the answer is no. And all of those strategies fail. And then on page 5, he finally realizes that his assumption is wrong. And he says, rather dramatically, finished, the end, my statement, is conjecture, is simply wrong. And although Schrödinger was rather fond of underlining words, it's very rare to see him underline things 3 times. So this was clearly a surprise to him.
Are all the vectors here in orthonormal basis?
Yes. So then he tries to prove that it is possible to have these multiple decompositions. And he very soon picks out a particular wave function for 2 particles. This time we have continuous variables. And he shows that this particular wave function that I wrote down there is an exact eigenfunction of the total momentum, and also an almost exact eigenfunction of the difference between the positions of the 2 particles, at least when this alpha factor in the integral is a very slowly varying function. So, he realizes at this point that if you have 2 particles in that wave function, if you measure the momentum of one particle, you can completely predict the momentum of the other particle. But if you measure the position of the first particle, you can almost exactly predict the position of the other particle. And indeed, that wave function is equivalent, or almost equivalent, to the one used by EPR in 1935, with a trivial change of reference frame, and by the fact that EPR do not worry about that alpha factor, presumably because those authors did not care so much about renormalization requirements as Schrödinger did. There's another document that I won't go into, but it's remarkable that at the same time, in another folder, he was deriving for himself the Schmidt's bioorthogonal decomposition theory, which tells you exactly under what conditions you can have these multiple bioorthogonal decompositions of a 2-particle wave function. So Schrödinger worked this out all by himself in 1931, and for the main part, just in a matter of 1 or 2 days after Einstein's colloquium. So here is what I think happened in that period, and why I believe that those documents are ordered in the way I showed them. Clearly, Einstein presented his photon box argument in November 4 in Berlin, and that version of the argument now involved a mirror, which presumably was not present in the 1930 Solvay conference. And although that mirror wasn't quite essential to the argument, somehow the discussion after the seminar got focused on the role of the mirror. Maybe Szilard raised a question about whether that collision with the mirror would be the source of an additional uncertainty in the argument. And so the discussion more or less shifted from the box to the mirror. So Schrödinger wasn't convinced of Einstein's argument, but took up that question about the mirror to boil down the whole structure of the argument to something simpler, And then when he asked himself, how would it work with particles, he even removed the relativistic photon from the discussion and moved to plain old non-relativistic quantum mechanics, just talking about two particles or systems, and found the entangled wave function, which would allow you to do exactly what later became the EPR argument. Now, we have, as far as I can tell, no evidence that Schrödinger corresponded to Einstein about his findings. In fact, since they were close colleagues, they would probably just have talked about it. I cannot imagine that Schrödinger did not discuss this with Einstein, because they were both very interested in the subject, presumably as the only two people in Berlin, for that matter. But precisely because they could have direct oral communication, there will be no written record for historians to show that that communication took place. What we do have is that after the EPR paper came out in 1935, Schrödinger repeatedly referred Einstein to their earlier discussions. So this first paper started with saying, I'm very happy that in the paper that just appeared in the Physical Review, you have publicly called the dogmatic quantum mechanics by its tailcoats, by coattails, about that which we discussed so much in Berlin. This time, of course, Einstein is in Princeton, or at least in the USA, and Schrödinger is in Oxford, so they have to write to communicate. Again, July 14 of that same year, he refers to, after you pointed out those things years ago in Berlin, we discussed them so much with hot hats in the seminar. Now, most historians who have discussed these letters, and there are several of them, have assumed that when Schrödinger mentions these discussions in Berlin from years ago, that they must have been about general issues about, since the fact that they were both unhappy with the dogmatic quantum mechanics in the Copenhagen interpretation. But I think that if you take a look at these unpublished documents which are in the Schrödinger Nachlass, those discussions entailed much more than just that. In fact, they entailed the entire structure of what later became the EPR argument. And this time, it wasn't Einstein who was inspiring Schrödinger, but instead it was Schrödinger who was teaching Einstein how to do this. And we also see that Schrödinger, in this earliest letter to Einstein after the EPR paper, he criticizes Einstein, albeit rather mildly, for the lack of sophistication with regard to the Schrödinger biochemical decomposition theorem. And he actually proves that theorem once again for Einstein's convenience, and said that he would have liked to see that also discussed in the EPR paper. And he finds it a pity that he didn't. There's another notebook in which he wrote down his earliest impressions after the EPR paper appeared. And there he was even more critical of Einstein and said that from the mere fact that by measuring one or another of two quantities of the system, we are stuck with wave functions that represent incompatible properties for the other system, we cannot construct a noose for quantum mechanics. We only obtain contradiction when we presuppose biochemical expansions. Although he writes about these mathematical issues to Einstein, Einstein's response is, "Das ist mir Wurst, I couldn't care less," and also he at that point he gave a completely different understanding of the notion of completeness than was in the EPR paper. But I'll leave that for another occasion. To conclude, although I do not wish to sow any doubt about the origins of the EPR argument in the sense that it has its historical roots in the photon box argument, but the photon box argument had many distracting loose ends and complications, and I would argue there's still a long way between the photon box and the actual EPR argument, which is so much cleaner and indeed focuses on the entanglement as the crucial issue. It was Schrödinger who actually recognized how you could strip down the photon box to its bare essentials within non-relativistic quantum mechanics and the crucial law for entanglement 4 years before the EPR paper actually appeared. And I would like to leave it at that, and thank you for your attention.
Okay, well, who dares? You.
Thanks, Jos, for a very interesting presentation. Okay. Anyway, brief comment and maybe two short questions. A comment is that I looked at Einstein's sort of proposals for quantum mechanical type experiments in the 1920s, and this notion that the end version of the published experiment or thought experiment actually is already present in earlier communications letters is very much the case there too. So there seems to be sort of waiting for this is the time to publish this particular version of the argument, which I kind of recognize. So I also have a recollection of Fine's account of this story, and two things I'd like you to clarify. As I understand it, I recall that when you speak about the historians that debate, sort of the lead up to the exchange of letters and the EPR in response to Schrödinger, as I recall, Fine claims that Schrödinger proposes certain sort of statistical interpretation type particles and boxes type accounts that then Einstein picks up on with EPR. Am I just wrong in my recollection of Fine on that? That's not what you're referring to.
No. There is a discussion in one of the letters of Einstein where he talks about boxes, and he has two types of interpretations of the situation, where one is statistical and he attributes that to Born, and one is non-statistical, which he attributes to Schrödinger, in which that's the view in which the wave function is regarded as something objectively real. But he uses the name Schrödinger there just to put a label on that position. That is actually Schrödinger's old or original interpretation of the wave function. But Schrödinger in 1935 has long abandoned that interpretation. And so he writes to Einstein and said, I do not adhere to that point of view at all anymore.
A different context then.
Yeah.
So my second question, I think a brief answer will suffice. I think part of Fine's account of this whole story is also that Einstein, in the end, says, yeah, actually, what's in the EPR paper is not really how I think about things.
Yes.
Right. So that twist of events, how does that impact upon sort of the Schrödinger pre-formulation of the? I mean, is that?
I'm not quite sure what to say here. Of course, when Einstein says what's in the EPR paper is not how I think about the issue, that must have taken Schrödinger by surprise. Schrödinger had read the paper and thought that that reflected Einstein's ideas.
And that's what they would have debated in Berlin. They would have agreed to. Right? It's the EPR paper is reflected in what Schrödinger wrote down in 31. That's what you've been presenting us.
Yes.
Right.
When Einstein presents the way he looks at things, he has particularly a very different understanding of the notion of completeness. And maybe I can, because I have some extra slides. In the EPR paper, there's only a necessary condition for completeness. So, in paraphrasing a bit that paper, the condition is that if the real state of the system is different, then it must be described by a different way. So it's a relation between real states and between theoretical descriptions. It's incomplete if, this is a condition of completeness. So if it fails, you might say this is incomplete. When Einstein writes to Schrödinger, he has a necessary and sufficient condition, namely that there is a bijective relationship between theoretical states and theoretical descriptions and physical real states. And this makes it possible for Einstein to use this double star conclusion, where it is possible to assign different wave functions to the same physical reality, which is something different from the previous claim, as a failure of completeness. But as Christoph later once introduced helpful terminology, you can have this bijective completeness in the terms of a one-to-one relation between real states and theoretical descriptions. You could have incompleteness in the EPR sense, in which if the real state is different, then it must be different theoretical descriptions. You can also have overcompleteness, in which there are many different theoretical descriptions that apply to the same real state. For Einstein, since he insists on a bijective correspondence, overcompleteness is also incompleteness. That's where he stops in his letter. He says, this is for me is the basic point. But overcompleteness is something that is far less interesting and striking than incompleteness. In fact, you will always have this in gauge theories, where you have many different theoretical descriptions of the same physical real situation. So, yes, Einstein had a very different understanding privately from the EPR paper. And if you ask me, I would say that Einstein's understanding of that was inferior to the EPR paper.
But it doesn't in fact impact on the prehistory of Schrödinger, because that's
No.
just shared in the same degree, in either position.
Shall we ask something
Yes.
else? I think Carlo has a question.
A short question, a short comment. The question is that in your slide there was only a couple of sentences in red, which is what Schrödinger wrote to Einstein. Do you think there was also complaining there? Schrödinger was saying, wait a moment, you cut me out from this discussion, I was there. That's the question. And the comment is, I think somebody should write a paper clarifying, as you did very well, what's actually going on with box of light. Because in the physics community, it's very much spread today, the old story that there is something puzzling there, whatever you formulate there, whose only solution is general relativity. And that's nonsense, because it would say that quantum mechanics is inconsistent unless there is general relativity, which is wrong.
Absolutely, yeah. So your first question was whether Schrödinger is complaining. Of course, I cannot look inside his head, but maybe it's certainly possible to read those repeated mention of these earlier discussions as in a sort of plaintive mood and saying, hey Einstein, you remember that we talked about this? But I don't think you should read too much in them. My impression of Schrödinger is that he was not hoarding his own results, and that he wanted to have his name on his, or be being referred to all of this. He never said anything more explicit about these issues. And then again, I also think that at that time, or at least that generation of physicists, it was not so essential or common to make appropriate references everywhere. So now the second question. Yes, there is, as I said, there are a lot of distracting discussions about the photon box. And indeed, one of them is the question whether general relativity must lend a hand to save quantum mechanics, or the uncertainty relations in particular, and that quantum mechanics could not stand on its own 2 feet. Those conclusions are indeed completely wrong. There have been other versions of the photon box argument which do away with general relativity. For example, I remember, I'm not sure who did that, but I think it's in Jammer's book, at least it's mentioned. You could present a version in which you, for example, you only use special relativity, and where you don't necessarily weigh the box in order to determine energy, and then there would still be a problem with, you don't know exactly in which Lorentz frame the photon box is transformed into, and therefore also affect the rate of the clock. But you could also do it without any general relativity. And in fact, it's not the case that Bohr illegitimately somehow brought in the redshift formula, because Einstein had brought in the equivalence principle to start with, and the redshift formula follows almost immediately from the equivalence principle. So the impression that quantum mechanics needs general relativity is wrong. It's only the case that you need relativity once it is brought into play from the very beginning. Does that answer the question?
Yes.
Okay, Jos. Well, we're on time now, so let's thank Jos once again. And move to our next speaker, Michael Duff. Let me in the meantime point out that we start tomorrow 9:30. That's half an hour later than is in the program on our website. And it is not in this building. It's in the Mari Gruber building. Consult the map.
It's a measurement.